All right, today we're going to talk about a totally different way of thinking about truth itself. It's a system called intuitionistic logic. And trust me, it's going to challenge some of the most basic ideas you have about what it even means to prove something.
So it all kicks off with this really simple but kind of deep question. If I tell you that some kind of mathematical object exists, like a number with some special property, how do I actually prove that to you? Turns out there are two totally different ways to answer that.
On one side, you've got the classical way, right? Proof by logic alone. You can just show that if the thing didn't exist, it would lead to some kind of crazy logical contradiction. So, boof, it must exist. It's a bit abstract, but then there's this other way. You can actually just build the thing. You can hand me an example or give me a step-by-step recipe for how to make one, and that's the constructive way.
And that second way of thinking, that idea of building it, well, that's the absolute heart and soul of intuitionistic logic. It demands what we call constructive proofs. It's not happy with just being told something is true. It wants you to show your work, to provide concrete evidence.
And this is the main idea, right here. A constructive proof is a demonstration. To prove there exists an X, you literally have to provide a method for finding or creating X. You can't just argue that it must be out there somewhere in the shadows. Nope, you have to bring it out into the light.
Now, here's where it gets really interesting. When you decide to adopt this super strict, constructive philosophy, you have to pay a price. You're forced to give up one of the most fundamental rules of logic, something all of us learn and just use without even thinking about it.
And that rule is the law of the excluded middle. Classically, we just assume that any statement is either true or its negation is true. It's either alpha or not alpha. There's no in between. It's either raining or it's not raining. Seems pretty obvious, doesn't it?
Well, intuitionistic logic hits the brakes and says, not so fast. To someone who thinks constructively, to claim alpha or not alpha is a huge deal. It means you must either have a constructive proof for alpha or a constructive proof for its negation. And what if you have neither? Well, then you can't make the claim. You just have to stay silent.
And making that one decision, wow, it causes a whole domino effect. We lose the law of the excluded middle, obviously, but we also lose the double negation principle. See, just because you can prove it's not raining, that doesn't count as a constructive proof of rain. And this means that classic move, proof by contradiction, where you assume the opposite of your goal to show it leads to nonsense, yeah, that's off the table too.
So if we're throwing out these huge fundamental rules, how in the world do you actually do logic? Well, logicians had to develop whole new systems, brand new blueprints for reasoning that could work inside these constructive limits. And the two most famous were dreamed up by a logician named Gensen.
First up, there's a system called natural deduction, or NJ. Its whole goal is to kind of model how we naturally reason, step by logical step. Its most powerful feature is something called normalization. Think of it like this. You write a messy first draft of an argument, and then normalization comes in, finds all the roundabout steps and weird detours, and just smooths them out, making the final proof as direct and clean as possible.
And the other system is called sequent calculus, or LJ. This one's less about mimicking how our brains work and more about the really deep, rigid, structural rules of logic itself. And that formal structure makes it amazing for computers when they're trying to automatically search for proofs. It has its own version of simplification called cut elimination, which does a really similar job to normalization. It just makes sure the proof is as tidy as it can possibly be.
So for decades, this was a really cool, but let's be honest, kind of a niche part of logic. But then, the people following these strict constructive rules stumbled upon one of the most profound and shocking discoveries in modern science, a connection they absolutely never saw coming. It turns out this whole demand for construction, for building things and having a recipe, it wasn't just a quirky philosophical choice, it was actually the blueprint for something completely different: computation itself. This connection has a name, the Curry-Howard isomorphism. And that word isomorphism is a big deal. It doesn't just mean they're similar. It means that on a deep structural level, they are the exact same thing. It's kind of like sheet music in a recording of a song. They look and feel totally different, but they represent the exact same piece of music. A proof in intuitionistic logic and a computer program? They're just two different languages for the same fundamental idea.
This is basically the one-to-one translation dictionary, and it's incredible. On the computer side, you have data types, right? Like integer or string. Well, in this logic, the formula you're trying to prove is treated just like a data type. So what's a proof then? It is literally a computer program that produces an output of that type. And here's the best part. Remember that normalization thing? Simplifying a proof? That is the exact same process as running the program to get your answer.
I mean, just let that sink in for a second. The very act of carefully constructing a logical proof is the same as the act of writing a computer program. This insight was a bombshell that completely revolutionized both fields, building this incredible bridge between them.
And this isn't just a history lesson. Intuitionistic logic isn't some dusty relic in a museum. It is an active, living, breathing frontier of research that is pushing the boundaries of math, philosophy, and computer science right now, today.
Right now, researchers are taking this idea in all sorts of wild directions. Some are trying to rebuild the entire foundation of mathematics from the ground up using these constructive ideas. Others are creating things called ecumenical logics, which try to build a unified theory where both classical and constructive logic can live together. And philosophers are using it to ask the biggest questions of all. Maybe the meaning of a logical statement isn't just if it's true or false. Maybe the meaning is the program, the proof that brings it to life.
Which leaves us with a final thought to chew on. The intuitionists insisted that to prove something exists, you have to build it. And that simple insistence accidentally revealed this deep, beautiful connection between proof and computation. So it really makes you wonder, if a mathematical proof can be a program, what else can be computed into existence?